I suggested in the last video, cardiac arrest is sort of like the fifth type of heart failure that can take place. It's separate from the other types of heart failure because it's really a different type of thing that happens, is where the electricity of the heart shuts down, and it can be very sudden. This is where they take the paddles and they try to shock you to reanimate the heart and try to get the rhythm going again. Before we talk about that electrical rhythm, though, it's important to establish the cardiac cycle first. So a cardiac cycle is one complete contraction and relaxation of all four chambers. I want to point something out here. That there's there's a lot of details in here, so it helps to contextualize them and put them into two big picture stories. The first thing that happens during the cardiac cycle is that the atria, which are on top, squeeze their contents downward. The second thing that happens during the cardiac cycle is that the ventricles, which are at the bottom, squeeze their contents upward. So if you keep in mind that the atria go first and the ventricles go second, some of these details will start to fall in place a little bit better than they would if you weren't picturing this entire thing in that way. Okay, so since this is a cycle, you can start anywhere in the cycle, but usually we describe ventricular filling or mid to late diastole first. So here we go. So with the first stage, ventricular filling, mid to late diastole, blood flows into the atria, and about 70 to 80% of the blood passes directly into the ventricles with no effort. It basically free flows in there. The atrioventricular valves are completely open. They do, however, begin to close toward the end of this phase. They will be closing, and the atria will contract and squeeze the residual blood down into the ventricles. I want you to think about whether at this point you have achieved ESV or EDV. Make a note to yourself. Write a guess down. Write it down and commit to an answer, and then you can always cross it out later, remember, and change it. Nobody has to know. Okay, the second stage of the cardiac cycle is what we call ventricular systole. At this point, the atria will be relaxed. The ventricles at this point will be contracting, and the atrioventricular valves will be fully closed. So while those atrioventricular valves are closed, which are the tricuspid and the bicuspid valves, they are closed fully. The ventricles will be squeezing upward only through the other two valves, which are the semilunar valves. So when the pressure in the ventricles exceeds the pressure in the arteries, the semilunar valves are forced open and blood is expelled from the ventricles. Okay, now at the end of this phase then, try to think to yourself, have we achieved EDV or have we achieved ESV? All right, again, write down your answer, commit to it. And then take a look at this. The last phase, phase number 3, is called early diastole. Early diastole is also called isovolumetric relaxation. At this point, the ventricles are relaxed, the valves, the AV valves are still closed, and blood starts to backflow toward the heart. At this point, you'll be closing the semilunar valves as they cup downward and allow for that blood to refill back into themselves. Okay. So that is the cardiac cycle, and there's lots of little details in there. There's lots of things going on again, but try to keep that big picture in mind there. We're going to go back now and think about how this all works. You remember that these things have to happen sequentially. In order for this to work correctly, you have to have 1, then 2, then 3. It has to work that way. So that is where we have the cardiac conduction system. And this is the electricity we're talking about. When we talk about a cardiac arrest, we're talking about this not working well, or perhaps not working at all, which would be actually a very difficult situation to survive. So this is what we call the intrinsic cardiac conduction system. There are autorhythmic cells. Remember them? The autorhythmic cells, these little gold guys here, the 2 beans here, and then all these strings buried within the myocardium. These autorhythmic cells are specialized to initiate and distribute impulses throughout the heart so that it contracts in an orderly, sequential manner. So the sequence of depolarization that we're going to be looking at here takes about 220 milliseconds, which is about a little more than a fifth of a second. And this uses autorhythmic cells in the following places. So let's start off here with the sinoatrial node, also called the SA node, the sinoatrial node. Super important. This is located in the right atrial wall, and this exhibits what's called a sinus rhythm, which is about 75 beats per minute. However, just so you know that at rest, the sinus rhythm is 75 beats per minute, but without any kind of innervation from the autonomic nervous system, you would actually have a faster rhythm of about 100 beats per minute. So the sinus rhythm determines your heart rate. The sinoatrial node is considered to be the pacemaker of the heart, and you can see that all arrows generate from here and kind of go downward and across and so on. No other region has a faster rhythm. So the sinoatrial node is the pacemaker simply because it's faster. It has a faster beat than anything else. All right, so before we go on to step 2, which is what's happening inside of the atrioventricular node, I want to say that you want to be really careful that you pay attention to what these black arrows up above. We tend to kind of concentrate on this story here, which is where the SA node is talking to the next guy in line, which is the AV node. But just so you know, at the same time, you have these black arrows here that are generating impulses and taking the impulse to muscles in the atrium. Remember our 2 big pictures here? The atrium must contract first. It must squeeze down and get rid of its blood supply in the stage 1 of the cardiac cycle. So before any of this stuff happens, all this gold stuff down here, which is very exciting, you also must have these impulses traveling throughout the atria. So as these impulses travel through the atria, you cause the contraction of these muscles and they squeeze down. Okay, so there is a 0.1 second delay here. This little arrow here going from the SA node to the AV node represents 100 millisecond delay. And then the AV node, the atrioventricular node, will now experience pacemaker potentials in response to the signal from the SA node. Okay, so the AV node is located immediately above the tricuspid valve, so it is still in the right atrium, the walls of the right atrium. And yeah, so that's the next place that experiences pacemaker potentials. That delay is super important. There's a reason I keep emphasizing this. That 100 millisecond delay is very important. It allows for all of the contraction to happen up here first, because you can see what happens next. Like if you look at the big picture, the AV node is in charge of like basically spreading a signal throughout all of the ventricles, and they are meant to contract second. The atria first, ventricles second, and so it's important that you have that delay there. Okay, next we have the atrioventricular bundle, which is located in the superior interventricular septum. This depolarizes about 30 times per minute. The right and left bundle branches here and here. The right and left bundle branches will course along the interventricular septum toward the apex of the heart, which would be right down here. And again, these guys would depolarize about 30 times per minute if they were not signaled to do so faster, which they are. They always are by the SA node. And then we have what's called the subendocardial conducting network, which used to be called the Purkinje fibers. I'm going to guess we're going to go back to that name eventually because it's so much easier. But the subendocardial conducting network allows for the completion of the path. So you could see it's sort of a network of branches that bring the electrical signal up through and they kind of complete the circuit up through the, they penetrate the apex. They supply the outer walls of the ventricles. They also, if you'll notice, take a look at this, they also supply the papillary muscles to ensure that the papillary muscles are contracting at the same time as the walls of the ventricles. And in case you hadn't put it together, you should put it together so that you are pairing what's happening here in the SA node, AV node, and all those all those other electrical circuits, you should be pairing them with what's happening in an EKG. So an EKG is shown here, the P wave, QRS complex, and the T wave. And if you look at this, I mean, I know it's a bear to kind of look over this figure, but once you kind of sort through it, it's one of those figures that helps you to really put the stories together. So spend some time on this. It shows in great detail exactly where you're at in the EKG, paired with exactly what's happening inside of the heart, which is actually quite useful. So spend some time taking a look at this figure.